Okay, so let's have a look at the Junior Certificate Higher Level Maths Paper 1 for 2018, questions 13 and 14. Okay, so below are four statements about three non-empty sets P, Q and R in a universal set U. Put a tick in the correct box in each case to show whether each statement is always true, sometimes true, or never true. P dash is just P complement, which means everything not in the set. Okay, so let's have a look. We have the first one here is P union Q. The cardinal number of P union Q is equal to the cardinal number of P plus the cardinal number of Q. Now this is actually going to be sometimes true. Now we have to justify this in the second part of this question, so I'll come back to that one in the next part of the question. So let's have a look at part 2 here. We have P less Q is equal to P intersection Q. This is actually never true. So if you have P and Q, so we have P and Q here, we want P less Q. So P less Q is going to be this area here. Everything in P, but take out Q. Is that ever going to be equal to P intersection Q? No, it's not. There's P intersection Q there. So you can't have P without Q and P intersection Q as well. They can't overlap. This area here and this area here are two completely separate areas, always. Okay, third one, P intersection Q complement is equal to P complement union Q complement. This is always true. So we'll just take that. So if we take P and Q here, P intersection Q complement, so we'll just put the universal set around it here. So P intersection Q complement, well, there's P intersection Q there, and the complement of that is going to be this area here. It's going to be everywhere outside the intersection. So it's going to be all this area here. So it's going to be everywhere except this area here. Now if you take this this part here on the right hand side, so we have P again and we have Q. So there's P and there's Q. If you look at P complement, well, P complement is going to be everywhere out here. So it's everywhere out here. So all of this here I haven't filled out. Okay, there's light overlap here, but that was a mistake. There is P complement is everywhere outside P. So this is P complement here. Now if we look at Q complement, then Q complement, just draw that underneath it here. So again, you've got P here, you've got Q here. This is P, this is Q. If you draw Q complement, then Q complement is going to be everywhere outside Q. So that's going to be this area here. And you can see that if I was to put this here on top of this here, the area that would, the only area that I wouldn't have shaded in is this area here in the middle. Everywhere else would be shaded in. If I took this diagram here, which is Q complement, and put it on top of P complement, everywhere would be shaded in except this area here in the middle, which is this area here in the middle. Remember, this is P intersection Q complement. So we would get the same area blank, we would get the same area not filled in, this area here in both cases. So this is always true. Now the last case then is P union Q intersection OR is equal to P union Q intersection Q union OR. This is always true. This is what's called a distributive property. We are distributing union over intersection, and this is always going to be true. So union distributed over intersection is always true. Okay, so part B then, it says, in the case of statement 1 in the table, justify your answer. So that's this statement here. I said I would get to that. Now, the cardinal number of P union Q, let me just write it out here. Actually, let me just move this up a little bit. So the cardinal number of P union Q is equal to the cardinal number of P plus the cardinal number of Q is equal to the cardinal number of P plus the cardinal number of Q. And what I set up here in the table is that this is sometimes true. So sometimes it's true, sometimes it's not. So let's just justify that. Well, if you take let's say our universal set here, and you have P here and you have Q here, and there's no overlap, P and Q here. So the cardinal number of P union Q here, in this particular case, it's going to be true, because whatever is in here plus whatever is in here is going to be equal to the cardinal number of P union Q. So for example, let's say I had an A in here and a B in here, a C in here and a D in here. Well, the cardinal number in this particular case of the cardinal number of P union Q is just 1, 2, 3, 4, and the cardinal number of P is 2, the cardinal number of Q is 2, so 2 plus 2 is 4. So you know the cardinal number of P plus the cardinal number of Q is equal to 4. So it does work here. Now if on the other hand there was an overlap, so let's take this scenario here where you have P here and you have Q here. Now in this particular case it's not true. So for example, let's say you've got an A here, you've got a B in here, and you've got a C here. So in this particular case, the cardinal number of P union Q is just equal to 3. 1, 2, 3. The cardinal number of P plus the cardinal number of Q, well, the cardinal number of P is 1, 2. The cardinal number of Q is B and C here, which is 2, so it's 4. So 4 is not equal to 3 here, so it's not true. So that's really it. So in the case where there's no intersection, it will be true. In the case where there is an intersection here, it will not be true. Okay, so that's question 13. Let's have a look at question 14. Question 14, use factors to simplify this fraction here. So you've got 2n squared plus n minus 15 divided by n squared minus 9. Okay, so we've got to use factors here. So the top here is a quadratic trinomial, so we can just factorize that like this. The bottom here is going to be the difference of two squares. This here really is just n squared minus 3 squared. So we can factorize the top. Let's see, that's going to be 2n times n. 15 is going to be, well, 15 can be 1 times 15. 1 times 15, it can be 3 times 5. 3 times 5 will work here. I can put the 5 here and a 3 here. And I need this one here to be plus, this one here to be minus. Minus times plus will give me a minus here. Just check that. 2n times n is 2n squared. Minus 5 times plus 3, minus 15. And if I do the 2 in the middle here, these two here, and add them, I'll get minus 5n. I'll get plus 6n. That'll give me a plus n, and there is a plus n in the middle. So that works. On the bottom here is just the difference of two squares, so I've got n plus 3 times n minus 3. So I've got n minus 3 here. Now you can see here that we've got these two terms multiplied, we've got these two terms multiplied, so this will divide into this, and I'm just simply left with 2n minus 5 divided by n minus 3. And that's it. Use factors to simplify, so we've done that. We've factorized here, we've simplified that. Okay, next one then. Now for all values a and b, where x is real, x plus a times x plus b can be written like this: x squared plus a plus b times x plus ab. So using this factor, otherwise, answer the following two questions. Solve the following equation in x where a and b are constants. Give your answer in terms of a and b. Okay, so we have x squared plus a plus b times x plus ab is equal to 0. Right, so what we can do here is we are told that all of this can be written like this here. So instead of this left hand side, we can just simply write x plus a times x plus b. So that's going to be equal to 0 then. Now when you multiply two numbers together and you get 0, one or both of the numbers must be 0. So x plus a must be equal to 0, or x plus b must be equal to 0. So solving these two then, subtract a from this side, you get 0. Subtract a from the other side, you get minus a. Or subtract b from this side, you get just left with x. Subtract b from this side, you get minus b. So our two answers are x is equal to minus a, or x is equal to minus b. And that's what we were asked to do. Give your answer in terms of a or b. So these are our two answers here. Okay, so let's do this one then. Last one then is just the same thing again. We have an x squared plus a plus b times x plus ab, and we want to divide that by x plus a. Well, again, we were just told in the first part of this question that all of this is just x plus a times x plus b. We've got to divide that by x plus a. So we have an x plus a on the bottom, which will divide into the x plus a on the top, and we're just simply left with x plus b. And really that's it. That's the end of this question, and indeed that is the end of paper 1 questions.